I will try to live up to that illustrious introduction. I have had friends actually make the joke that they've tried to watch my presentations on sort of 2x or 5x speed, and then it gets dizzying, so then they like lower it down to like 0.5x or like 0.7x or something like that. I think I talk way too fast. So I have a lot of stuff I want to cover here. Let's see if the presentation is it going to cooperate on things. Hopefully I can actually get onto the internet because that will make this more fun. All right, so what I'm going to do here, I don't have any slides and I don't have any generative AI. Instead what I have is a very basic editor buffer that doesn't even have metals or like LSP or anything like that. And what we're going to do is we're going to take this code. So actually first thank you. Is that good? Good? Everybody good? Mm-hmm. Okay, cool. If there are questions at any point or things you want to see dived into more, or if I just didn't make any sense, which is probably going to be 90% of this, please do interrupt me. I think that's actually going to be way more fun. Because what we're going to do is we're going to start with this code, and we're going to go all the way down to how this works. So every little nitty-gritty detail, or at least as far as we can get in 45 minutes, we're going to see what actually makes this tick. Because the code that you see on the screen is actually doing a lot on our behalf. And I want to kind of unpack that and pull the curtain back on the magic. So we're going to look at coroutines, we're going to look at schedulers, we're going to look at threads. If we have time, we're going to look at syscalls, we'll look at HTTP parsers and header implementations, streaming algorithms, those whole sort of stack all the way through, type classes and all. So hopefully that's not too ambitious for 45 minutes. But yeah, so before we get started, this code that's on the screen, does everybody kind of know what this does? Who wants to take a guess of what's actually happening here? Of course you volunteered, so now you're on the spot.
Well, I guess it will be calling this URL, find_net, get a string back. In parallel, we've got this print line attempting request, and once everything is completed, then we display the string that we got as a result.
Basically 99% correct. So it doesn't happen in parallel, but that was really good. I could make it happen in parallel, and actually that would be kind of fun. I might just do that. But just so we're all on board. Hey, cool, my internet works. So down at the bottom, I did curl the URL. It just returns hello world. Right? So there's just an HTTP server out there in AWS somewhere giving us tags. That's all I really wanted to do here. And what this will do, this will actually call that. So let's actually, just for fun, we'll make this happen in parallel. So I'll just use a different operator here. Now we sort of all know what's bad about doing live coding and making sure that this works, but let's see, attempting request, and hey, it actually did work. Okay, so it's kind of trivial, but we'll get to that. So what's happening here, so we do the print line here, attempting request, and then in parallel to doing the print line, so we sort of kick it off at the same time, we race against that, make the HTTP request. You can't really see the parallelism because print line on the local system is much faster than going over LTE to talk to AWS and come back. But I don't know, maybe if we made 2 requests, we could get them in kind of different orders or something like that. Anyway, that's not the point. The point is we're going to figure out what's going on here because there's actually a lot that's happening. There's a lot that's happening here, and it's really very hidden from you. And you don't really see what's going on until you pull it apart. So let's dive in. So the first thing we have to do is we have to figure out how this code is running in the first place, okay? Because it's Scala, right? Scala runs on the JVM, and at least this version of Scala runs on the JVM, and the JVM expects a main method as the entry point to the application. So when I actually Scala CLI, which is what I'm using here to run this, doesn't have any particular knowledge of cats and fact, right? So it's just gonna use the JVM to run a main method. So there has to be a main method here somewhere that's the entry point for our application. And clearly we don't see it because just naming the object main does not cut it. So how is control flow even getting into the process? Maybe we should start there and work our way outward. So let's figure that out. So the main place this is going to be hidden is in the IO app class. Okay, I think it's actually a trait, but so we're extending that with our main function and our main object, and hopefully inside of there we'll find ourselves a main method. that maybe delegates to this run thing somehow. That would be really, really helpful. So like, let's go jump to that. And oh, there's actually several different versions of it. So we're gonna like limit ourselves down to the JVM version. So Cat's Effect actually runs on Scala Native, Scala.js, and JVM. And so you can actually do this cool thing where you could write code and sort of cross-compile it to whichever one you feel like when you want to confuse your project managers. But in this particular case, we're using the JVM one because we're not being tautological. So okay, we're here. This is great, and there's like lots of like comments too. So this actually kind of seems somewhat helpful. So maybe we're kind of in the right place. Let's look first. Is there a main method in here? Heavens be praised. There is. Okay. So this is where the code starts. Okay. So I'm going to take this and I'm going to shift that over there. So this is where the entry point to the application actually is. It's this thing that I have on the screen on the left. I'm going to hide the terminal to ourselves a little bit more space. And this is, as we prophesied, doing actually quite a lot of complicated things. So let's very, very quickly start like walking over this. Most of this we're actually going to be able to skip, which is really, really good because there's a lot of shenanigans here. So the first thing that happens, we basically start looking at the thread IDs. Now this is not a thing that you do in normal code. The reason Cat's Effect is doing this for you is because SBT has this terrible feature where when you call run, by default, it doesn't fork a new JVM. Instead, it runs on the same JVM, which means that you're not actually in a sandbox process. You're just on like some threads that are like sitting in the SBT heap. And it turns out that there's actually a lot of bugs with this, and it does really, really, really weird things to your code. So Cat's Effect does its absolute best to detect this situation, and the way we detect it is by getting the ID of the thread. Turns out that the JVM assigns thread IDs sequentially from 1. So if you run inside of SBT, you won't be 1 because SBT has thread 1. This is how we detect it. And we actually, I think we give you, no, we don't give you a warning on that. That's like in a different version, I guess. So we should give you a warning on this because it's just never what you want. Like it's very, very bad. But we try really, really hard. We try really hard to make it work. Oh, actually, we do give you a warning. Here it is. All right, back to where we were. So, okay, moving past all of that, the very next thing we do is this terrifying looking code, which is basically initializing an IO runtime. And we're going to come back to what that actually means in a second, but IO runtime is basically the thing that manages, it sort of has all of our threads and stuff, right, configurations and things. So just from this point on, know that the runtime field has the IO runtime that we are using, okay, and that's going to take care of a whole bunch of stuff for us. So we've done that, warn the user. There's a whole bunch of stuff here about like tracing, which we're going to completely ignore and pretend that it doesn't exist because it's really, really complicated. And now we work ourselves down to the fun stuff. And I know it's fun because right here, what I have highlighted, that's what we call run, okay? So remember, in our code over here, this run thing returns the IO unit. This is the way we defined our program. So we got to the point in our main method where we finally called run and got the IO that the user has defined. So this is great, actually. We're like making a lot of progress. So what we do is we call run with the args to list, and then we get that as an IOA. In fact, I know this is going to be of type IO exit code, but that's just what it is. But this IO is not actually running yet. So for those of you who've actually used Cat's Effect or like any of these systems, like IO is a description of a program. It's not actually a running program, right? This is why the question of parallelism is actually kind of subtle with IO. Like you really have to ask for it in order to get it. So the very next thing we have to do is we have to actually run this IO. We have to sort of make it go. This is the whole thing that we tell you not to do when you're writing programs with IO. Well, somebody has to do it, and that somebody is us. If we just ended the program and exited main at this point, then your program would never do anything. Like the box would get one, basically. So okay, so what are we going to do now? We got some workarounds, some bugs in Scala. This little thing right here, this JVM starvation metrics, we'll dive into this in just a second because it's kind of fun. But basically what we're doing at this point is we're wrapping like some other code that we control around the IO action that the user wants to do, right? So it's a surround. So what does that surround function do? Just real quick, it looks like it calls use around this thing. We'll come back to use, but this is our IO action, right? Use, we're inside of, this is the resource class, so we will come back to this one. But surround's going to be meaningful later. So basically, starvation metrics, we'll look at that, does this thing, we surround the IO action, but really the IO action is like inside the body of the use, so this is what's actually going to be run. And now we have to actually make it go. And we do that with this method right here. unsafe run fiber. Okay. Is everybody following so far? Because I've been like bouncing around a lot. Okay, cool, cool. I see nods and blank stares of terror. Okay, so unsafe run fiber. Now, those of you who've used I/O and called the methods that are sort of prefixed by unsafe, first off, stop it. Second off, you probably know that unsafe run fiber is not actually a method you can call. Like, it's not there. And the reason for this is unsafe run fiber is totally in journal implementation detail. So let's dive into that. Like, this is private to Cat's effect. We need it. And it turns out that this method is actually the basis for all of the other unsafe run methods. So here's unsafe run or unsafe to future cancelable. Here's unsafe to future. Here's unsafe run to forget. Here's unsafe run async, which I think is kind of clear. Like, it just calls unsafe run fiber. So all of it is unsafe run fiber. Okay. So what is this doing? Well, so this is in I/O, just to be clear. We're like in the I/O class at this point. So this pointer that we have access to it, this is the program that the user defined, okay? So more or less, this is the value of the I/O on the right. That's what we're dealing with. So when we say unsafe run fiber, this is what we're trying to run. So what do? Well, the first thing we do is we create something called an I/O fiber. So what this function is going to do, more or less, is it's going to create a new fiber, which is a concept that exists in Cat's effect to represent a coroutine. We'll talk about that more in a second. But it's going to create a new fiber for your main code. Okay? We sometimes call this the main fiber, even though it's never actually named anywhere except the documentation. And this main fiber, again, it's not actually doing anything when we create it. It's just a data structure to kind of track all of this stuff. But what we can do with fiber that's very, very special is we can ask it to run. Like, we can give it to the runtime and tell it, go. This is actually what happens when you call the start method or the background method or any of the parallelism stuff that's inside of Cat's effect. That also creates fibers. It actually just creates more of this same data structure. So the way that we make a program go in Cat's effect is we start a fiber and we hand it, or we create a fiber and we hand it off to the runtime. Okay? Now the fiber that we're creating it's based on this, which remember that's the program that we're trying to run. And it has some of the attributes from that I/O runtime thing that I told you to ignore earlier that we created. So now we kind of have to actually care about what this is doing. But before we get to that, real quickly, this is kind of an interesting part of it. So this is all in the constructor for I/O fiber, right? So we'll look at I/O fiber in a second. I/O fiber takes that function that produces, this is actually going to be an outcome I/O throwable A, like whatever that is. So I'll just give you the type there. So what is this outcome? This outcome is the result of running the main fiber. Okay? And this is useful. This is important because what we have to do when we finish running the main fiber is we have to actually give it back to the user. So if we complete successfully, for example, we have to get the value out of that main fiber, and we have to return it back, right? Like produce that back to the success callback that we have up here. In the case of the main function, that value is going to be unique, so it really doesn't matter. But like this would actually matter if you were calling unsafe run safe or something like that somewhere else in your code. If we fail, we also have to hand that back, and if we hand it back, these functions are going to get invoked. Okay, so this is what happens when we fail. We actually, we're not printing the exception. Like this is a throwable here. Like, what is going on? Well, let's trace this through. Okay, so we put this on a queue. I promise we're going to get to I/O fiber, by the way. So just like keep that on your stack. Like we're in the business now. Okay, so we take the throwable and we put it onto the queue. Well, what is this queue thing? Okay, well it's a workaround for Scala hash 1, 2. Okay, now what is it actually? All right, so that's up here. It's apparently an array blocking queue with a helpfully arbitrary constant. So why do we have an array blocking queue of any ref, of all things, in this layer of the stack? Well, the reason we do this is so that we can pull on it down here. Okay? So we're still in the main function, by the way. Like the main function in I/O app, it kicked off this unsafe run fiber, and then that is happening in parallel while the main function goes off and does some more bookkeeping. And the bookkeeping that it does is it loops on while done. Okay, so this actually looks promising. Clearly the main function is just going to wait for the fibers to complete so we don't kick them off and then immediately kill the process. While done, take from the queue. And what it takes from the queue, it will now go try to do something with. If it's an exit code, which it knows is the return result of run, well then it shuts down the runtime and like system exits and like does all the things that you would expect it to do. If it's not an exit code, wow, interesting things start happening. So here's a throwable, for example. If it's a throwable, now we print the stack trace, and then we halt the runtime. So this is a slightly different code path. Does anybody have a guess as to why we would want to handle throwables coming back from IO Fiber a little bit differently than we handle normal results? Anybody have any thoughts on this? I'll give you a hint. It has to do with weirdness of the JVM.
Is there like non-recoverable exceptions?
Yeah, non-recoverable exceptions is exactly the answer. So, story time with Daniel. So, about a decade ago, I was working on a system where it was all built inside of Future. It was this really, really complicated thing, and most of what it was doing was like arithmetic calculations and I/O. It was an OLAP database, basically. And when we deployed it in production, it would run for quite a while, but then eventually it just started giving us like really odd results. And not like odd like errors, but odd as in like 2 + 2 = 5. And with like floats. Like it wasn't even like objects or something like that. So it was very, very like literally arithmetic was broken. And we were like, what is happening here? So I was not able to find this bug, by the way. It took my colleague like hero moding for like 3 weeks, I think, where he didn't sleep at all. But he finally traced it down to the fact that what had happened was several days before we noticed the error in production, we had run out of memory. There was an out-of-memory error that was thrown, and then Future caught it. So at this point in Scala's lineage, Future actually caught fatal errors. The reason it doesn't catch them today is because I complained to Victor and he changed it. It was because of this bug, okay? So anyway, so the error was caught, and when you catch an out-of-memory error on the JVM, you can just swallow it and try to move on. But when you do that, you are out of spec. So the JVM is actually very, very clear if you look in the spec. Like if you catch and try to recover from some of these errors, the heap is in a non-deterministic state. And if this happens while the garbage collector is doing a cycle, well, its pointers might be in the wrong place. And so now your heap pointers are actually wrong. And your program is just blithely continuing on, assuming that everything is fine. So anyway, TLDR, don't catch fatal errors. They're really, really bad. And if you try to catch them and then wrap them up in structures and report them back to users, that's not going to work. So, to your point, we want to give fatal errors back to users. We don't want the application to just silently die. But we can't catch and recover them, and we can't allocate to carry them around between threads. So we have to treat them very, very, very specially. And that's why this is a separate code path. This is also why it's an array blocking queue rather than a linked blocking queue, because array blocking queues are pre-allocated, and it turns out that it's safe to access them after an out-of-memory error. So, yeah, welcome to problems that Cats Effect are solving on your behalf. Why is this a queue, though? Okay, so we still haven't really answered that question. Well, the reason that this is a queue is this thing right here, runnable. Okay, so if there's something of type runnable that ends up on the queue, we actually just run it. Well, okay, that's great. How does something runnable end up on the queue? Well, let's find out. It turns out it happens right up here. Okay, so please don't ask why we have that line. There's a reason for it. But anyway, what we're doing here is we're creating a new execution context that we call main thread. And what we do is we take the runnables that are passed to it, and we immediately put them on the queue, which is then picked up by that hot while loop on the main thread. And so this is actually a nifty little trick. Most of the time in Cats Effect, your program is running on a thread pool that Cats Effect controls. Which means if you're dealing with some native library, let's say CUDA or OpenGL or something like that, which actually really cares that you're on the main thread, the real main thread, not the main fiber Cats Effect thread, well, how do you actually get back to the main thread if Cats Effect is in control of it? The answer is, you do this. You can actually eval on your IOs onto the main thread, and it will run the IO on the main thread, which is actually really, really cool, and don't do that. Okay. That was a very, very long digression, but like now we understand how errors work, right? So, okay, where were we? we were talking about I/O fiber, the different cases that come out of the outcome. Okay, the outcome is the result of the I/O fiber, and if you've ever done join on a fiber, you might, or guarantee case, you might be familiar with this data structure, right? It's the thing that represents either canceled or errored or complete. So we see that right here. And we see this runtime compute thing, okay? We see it passed to the fiber, and we also see it used down here with a line of code that looks suspiciously like make the fiber go burr, okay? And indeed this line does make the fiber go burr. So what is actually happening here? Well, let's look at what is the type, what is IO runtime? Let's go to IO runtime, and fortunately there are not a million versions of this thing. So IO runtime contains these things, all right? So this is the constructor for IO runtime, and compute is actually one of these. It's an execution context. So this is actually great. Like, this is starting to look like something that maybe we understand, right? Like, execution contexts are thread pools. Thread pools run tasks asynchronously, like we can sort of hand them off to them. That's exactly what we're doing here. So fiber is clearly a task then. And actually, as it turns out, fiber extends runnable. So like, it literally works, right? So running a fiber is putting it on this thing. Now, we will come back to what is in the execution context, because that's fun too. But for right now, let's just remember that execution context, thread pool, it's inside of here. Everybody looks confused. Have I lost everybody yet? Nope, nope, nope. Okay, we're gonna dive even further. IO fiber. I promise at some point we'll talk about HTTP again. There's a method to the madness, I promise. Okay, so IO fiber also has like a wonderful number of comments, which are apparently talking about things that are terrifying for this room. So we're going to scroll down. If you do want to look at this code, by the way, I highly recommend it. Like, I actually think IO fiber is pretty easy to read. It's just very weird. So like, you know, spend a few weekends on it. So IO fiber, we already know that it takes the IO that we're trying to execute, right? So remember when we started with the code on the right here, this run, and this code right here, this IO, it's finding its way into this thing right here. So this is the IO that we're trying to run. And this execution context, this is the IO runtime compute, okay? This is the IO runtime itself. There's various reasons why we do this. And this is the callback that we're going to run when the fiber is complete. So this actually is kind of almost starting to look like a semi-reasonable structure, all right? Now, we'll come back to what all of this stuff means in just a second, because I think it's actually easier to follow the control flow of the code, right? So when we take a runnable, which is what this is, it extends runnable, and we pass it off to an execution context, that execution context is going to invoke a very specific method. It's going to invoke run. So this is the very first moment where our code over here, our IO, is actually literally running, as opposed to just in the process of being constructed, okay? So we finally made it to the spot where we do real work. All right, so what does this work? Okay, read variable. Well, this is already starting real promising. Let's talk really quickly about this stuff, because it's like, I think this isn't as widely known as it should be. So when you're working on threads, okay, and your underlying hardware has more than one physical processor. We don't tend to think about that in those terms anymore because AWS pretends that physics doesn't exist, but it really exists, I promise, right? Like, there's real silicon somewhere that's running your code. When you have two threads that are running on two separate physical processors, they're dealing with slightly different versions of a cached memory space, right? Like, we kind of have this notion that when you access main memory, it's just like a soupy pool and you go talk to it and it's infinite because Bezos will provide. But like, really, it's actually kind of like more complicated than that. And what the processors will do is they will page little parts of your memory into these cache layers, right? This is the L1, L2, and L3 cache, especially those latter two. And then there's even sort of lower level bits of caching that happens as your code is operating on bits of memory, which is in the registers of the CPU itself. Now, the L2 cache, most of the L3 cache, and of course, all of the registers are completely isolated between the processors. So if you have some code that's running over here that, say, writes to a variable, but that variable is contained within a register, and it's only on this processor, if you've got another thread over here that's reading that variable, it will not see it, okay? If you've ever seen the @volatile annotation or the volatile keyword in Scala, and you wonder, why are people doing that? It's because this is a problem, right? And so what volatile does is it basically says every time you write to that variable, we're going to push that all the way down to the main memory. And then every time you read from that variable in this other thread, you're not going to read from a register, you're going to read all the way from main memory, which is incredibly slow, so you generally don't want to do it. What that is doing mechanically under the surface is introducing something called a read barrier and a write barrier. Okay? Now, if you use sort of concurrency primitives in C++, you'll actually see these things much more explicitly, and it gives you a lot more control over it. The JVM is kind of doing this for you by magic. In Cat's effect, we unmagify the magic that the JVM is doing, and we do it for ourselves. And we insert our own read barriers and our write barriers, and we do that, now we're really in the nerdy details, but we do that by reading an atomic Boolean. So in IO Fiber, there's an atomic Boolean suspended, which I think is all the way at the top here. Oh, we actually extend the atomic Boolean. That's great. Yeah. So we're reading this. Okay. So there's an atomic Boolean that we read to create a read barrier, and we write to this atomic Boolean whenever we want to create a write barrier. This is the primary way that we handle memory fencing for fibers. Now fibers, now we're in conceptual land. Fibers in general are going to live on a single thread while they are running. So once you start running a fiber, one thread has it until that fiber is done. And by done, I mean it gets to a yield or like an asynchronous call or something like that. So some reason that it's just going to get off the thread, at which point maybe another thread could pick it up, right? And there's sort of the process of moving over there. There's a really subtle little thing though, which is number one, we have to make absolutely sure that no two threads are running the fiber at the same time. There's no race condition where like somehow two of them got it. And number two, sometimes there can be like strange scenarios where a third thread comes in. So we actually have to be really, really careful about this process. But by being careful about it, if we can sort of wrap up those guarantees in a very, very careful way, then we can make a bunch of assumptions throughout the rest of the fiber because we know it's never going to leave its host thread. Like when we're running, it's going to be on one carrier thread, which means we don't need to use volatile. We don't need to use atomics. We don't need to do anything. We can just pretend that there's a single thread in our JVM inside of this fiber. Because from the perspective of the fiber, there is. And the only thing we have to do is very carefully touch this atomic Boolean in like strategic places. Yes?
Is it resilient to the underlying memory model that works on the CPU itself?
That is an awesome question. Is it resilient to the underlying memory model that underlies the CPU itself? Well, someone's been doing the homework because what you are aware of is that there's two major memory models that you might find in modern data centers. There's x86, which uses a memory model called total store order. Very, 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 very strict. And then there's ARM, which is totally loosey-goosey and very, very, very lenient. And all sorts of stuff will happen on ARM that x86 would never expose you to. Right? It's super, super annoying. Talk to me about M-series chips to see magic on this stuff. Anyway, so the question is basically, are we resilient to that? And this is a really good question because memory barriers behave differently on these two architectures. Total store order means you don't have to care about memory barriers so much because any barrier just sort of publishes the whole world and you're back in main memory, whatever. The answer to your question is yes, it is resilient to it now. Let's go down here. All right, I think it's not, let's see. It's not, let's just look for suspended. I think it was by read barrier. This is literally how I navigate this thing, by the way. So the problem that we have, I want to do, it should be where we write to it. Here we go. Okay. So here's a pair of functions that should tell you everything you need to know once you do sugar them. So suspend is what gets called by the fiber when it gets off of its carrier thread. Okay, so when we yield or we do something like that, like we're getting off the carrier thread, so we're gonna suspend the fiber. So this doubles as your write barrier. Resume is what happens when we get back on. Okay, so maybe we've got an asynchronous callback that sort of resumed the fiber, like the network traffic came in, something like that. So what we do is we do a get and set false on suspended, and then we return that Boolean, which is a very, very, very bizarre way of writing compare and set. Like really, semantically, what we're doing is suspended, compare and set, true, false. Like you were suspended, now you're not. And the reason it has to be a compare and set is because we want to make sure that we're the only thread that resumed this fiber, right? If another thread is trying to resume it at the same time, it needs to fail. So that's why this has to be a compare and set. Except, on ARM, as it turns out, compare and set is not always a write barrier. Sometimes it is, but not always. Also, it depends whether you're on like ARM 4 or ARM 6 or ARM 64. That varies.
Apple as well.
Apple as well, yep. Again, the M series chips do a lot of weirdness around this stuff. So, so we discovered this bug because this used to be compare and set true, false. And everything was great until some wise guy got the idea of running our unit test suite on an AWS Graviton v1 instance, and it did not work. Fun fact, this would have worked on AWS Graviton v2 mostly by coincidence. But like, it doesn't work on v1. And this took forever to track down. But it basically comes down to the fact that if you use a compare and set, and the cast fails, okay, so you're not going to do a write. On x86, because of total store order, you get the write barrier anyway, because x86 is like that. But on ARM, prior to ARM 64, it's not an intrinsic, and it's done with two separate atomic operations, and if the cast fails, you do not get the write barrier, it doesn't publish the memory, and everything is inconsistent and your whole world blows up. So the solution to this, courtesy of Victor Klang, is get and set false, which I literally had to write out a truth table, but it turns out to be exactly the same thing. But the thing with get and set is it is unconditionally writing, and so you always get a write barrier. That was an awesome question. Okay, we still haven't run our code though. Back to run. Okay, so we do a read barrier. We've now got to line 2 of this function. What are we doing now? Well, we're looking at something called resume tag. Okay. Now let's pause and think about what IO Fiber has to do here. Okay, so IO Fiber is managing the state of your fiber, and actually, if you're using cats effect and you call like .start and you get that IO of fiber, that's the sort of the production, right? And you look at if you FlatMap on that and you look at the fiber that's in your hand, that it has the join and the sort of, you know, the cancel functions, right? Like that is actually an instance of this class. Okay, so you could cast it and do terrible things if you really wanted to. Don't do that. So this is a thing that's going to live for a long time. It's going to get on the thread. It's going to get off the thread. What that means is that conceptually, this is going to move through the state of our program, or at least the state of our fiber, as it lives. And then we're going to take it off a thread, and we're going to have to bring it back on, and it's going to have to pick up its place in the queue exactly where it was in the program. So how do we do that? We do that with resume tag. So what resume tag corresponds to is a little byte. And that byte can contain many different values. At some point, I'm going to get out of cats effect land, because this is like so far in the weeds. This byte basically says, okay, when we come back from the thread, what are we going to do? And in the default case, it's just you're going to execute the IO that you have. But maybe you were in some sort of different state, where you were like doing an async callback, or maybe you were yielding, or something like that, in which case you might want to do something different. But in this exact case, we're going to be right here. Okay. By the way, you'll notice this @switch annotation, and then we like actually do like the literal specific numbers in here. This is because Scala will compile this to a special data instruction called a table switch, and then as long as the cardinality of your table switch is more than 7 and less than, I think, 19, but it might be 17, the hotspot will then generate a very particular set of assembly, which actually is much, much, much faster. So it turns out that if we had fewer than 7 cases here, this would be slower. For reasons. Okay, so execr. What does execr do? Well, execr is going to read, so I jumped ahead just a little bit, but it's going to read the resume IO. And remember, resume IO was the variable that we passed into the IO fiber constructor. So this is our IO program, right? Remember, it's this thing. We found it, it's right here. We take it and we put it into just this, okay? So we're putting it into a little variable. We null it out so that we don't do anything stupid with it afterwards. Actually, this is mostly to remove memory leaks. So we're not pointing to like a part of a continuation that we've already run. And then we start going. We call run loop. But before we call run loop, we set up a couple of data structures. Okay? And this is where things get really fun. This will probably be the last bit that I talk about with IO Fiber, and then we're going to go on to other parts of the ecosystem. But like, I wanted to get to this bit because this is really, really fun. If you have ever wondered how continuations work, okay? Sometimes they're called continuations, or Go routines, or fibers, or like, there's a bunch of different names for them, green threads. They're all basically about this. Like, and everybody's implementation actually looks basically identical because I don't think there's any faster way of doing this on modern hardware. But basically what you're going to have is you're going to have a continuation stack which tells you, what am I supposed to be doing next? Is it like a flat map? Is it the second end of a flat map? Is it like a, what do I need to be doing right now, right? So it's kind of like a program counter, sort of. And then you're going to have some state, okay? So we call this state, and I'll go to the actual types of these variables in a second, but you're going to have some state, which is like, this is the sort of function that was passed to FlatMap, and now I need to run it. Or this is the IO that was like the second parameter of this function, so I need to pull it out and like actually operate on it, okay? So fundamentally speaking, what we're doing here is we're taking data that was on the stack and we're putting it onto the heap, and the part of the heap that we're putting it onto is right here, object state. And so these are our instructions, these are our object state. So we're going to look at object state really quickly because this is byte stack is like or very, very similar, but this is easier to understand. So what this is just a dynamic. Oh, I went to the wrong implementation. JVM. So what this is just a dynamic array. Okay, we've got an array that starts off at size 16. We keep track of where we are in it, and then every time we push onto it, we call this check and grow function, which does exactly what you did in your CS201 course. Like, we check the length, we double it if we're the wrong size. And we never actually shrink these sizes, so like, there's actually this interesting property in the continuations where if you've got a long-running fiber, it sort of like has this warm-up period where it's allocating and allocating, like getting to the right size, and eventually it just kind of settles and then stops allocating, and it will just run more or less forever without allocating at that point. It's kind of nifty. Again, literally everybody's implementation looks pretty much like this. Like some people do struts if they're like in languages like Go or C or something like that. Some people separate it out into two columns like this. Same idea. So now when someone says coroutines, you know what they're talking about. They're talking about this. Okay, so let's go back to exec_r, and then we're going to jump to run loop, and then we're going to pop all the way back up the stack to review what we learned, and we're going to look at some other pieces. Okay? So exec_r said the resume IO is in IO. We're going to pass it to run loop along with a bunch of other parameters, which I don't know, I guess probably matter. We initialize these data structures in our fields, and then we call run loop. So what does run loop do? Run loop takes the current IO and begins actually interpreting it. And the very first thing it does is sort of like checks, are we done? You know, we're not done in this case. Do we need to like do some auto cancellation and like auto seeding? Like we're not going to do any of that stuff. We're just going to move past this pretty quickly. What are we going to do if we're actually doing work? Which literally is this first line right here. So we're actually trying to do some work now, right? We're going to hit this line right here. We're going to call cur.not.tag. Well, what is tag? I mean, you should mention it. So let's look at the implementations of IO. So when you call FlatMap, or you call like pure, or you call any function on IO, what it's going to look like is something a bit like this. Like here's pure on IO. It just literally creates like new pure value. Okay, this is what's happening. If you call FlatMap, it's doing the same thing. Like it just calls new IO.FlatMap. So what is actually happening inside of here? So this is a case class, and it has inside of it a def tag. And that tag, as it turns out, I think it's a byte, if I remember correctly. And each one of these has a different value. And the reason we're going to do this is because when we come down to here, this is faster than pattern matching. So if we had done a pattern match, then every time we hit this line, we're going to do a linear scan through all the different cases. And there are actually quite a few cases inside of IO. This way, we're able to do that table switch thing again, and we're able to generate like the hotspot assembly code that's like exactly perfect because we're sitting in the sweet spot of like integer ranges, and everything's actually going to work out really well. So this is pure. Wow, somebody removed, oh no, no one removed my comment. So the idioms of like walking through this basically are like, you have some sort of case,
And then the very first thing that's going to happen in the body is it's going to cast her knot to whatever type it knows it is now, because it's a tag. So now we have an IO of pure. Well, an IO pure has a value inside of it, so when we're interpreting a pure, all we have to do is get the value out and then pass it along to the next stage of computation, which we do by calling this succeeded function. If it was a different case, like say an IO of error, which has a throwable inside of it, we would have been in tag 1. And in tag 1, we cast it to an error, we get the throwable out, we check to see it's fatal, and then we call fail. Yes?
Not like the earliest version of first iteration when we had 3 monads in right direction, and it was missing out with the G at the time.
Yeah.
So is that the optimization that allows us to actually gain performance back compared to back in the day? First time we were doing pattern action on FlatMap and doing the branching manually.
Yes, so this does a couple of things relative to that. So first off, this code doesn't allocate. Like once our array stack grows up to the right size, there's 0 allocations in here. The only allocations are like creating the IO. So that's a huge difference from the way that we used to interpret free monads, where it's like natural transformation and blah, right? It was terrible, right? So that's the biggest thing. But then the second thing is, this code is, as I've been kind of alluding to, a lot more sympathetic to the way that Hotspot wants to work. And ultimately, we sort of boiled down a bunch of different things in here into a nice shape. Now, this is obviously, it's way too large for inlining, but that's okay. This will be like our one non-inline function. Everything else is going to inline. And nothing is polymorphic. Like, we're not calling polymorphic methods, except this one. So there's one invoke virtual right here. It sort of gets the thing back. And then we table switch jump from there. It's very, very branch prediction friendly. It's very, very pipelining friendly. There's actually a lot of things all the way down to the CPU that line up really, really well with this. When we were writing free monads like 10 years ago, we were like, lol allocations, whatever, right? Like we just didn't think about that stuff. So this is probably the fastest way that you can write a free monad on the video. Cool. All right. We might actually call it quits here because I think I'm supposed to stop at 8.
Yeah, but you can, it's they wanted you to keep going.
Oh, okay, okay.
Honestly, and I just wanted to be official here, it's your meeting, right? We wanted to keep it at 2 hours because we thought 2 hours was a lot for in-depth technical discussions. But you guys look like you're following him and you want to keep going, so let's keep going.
Yeah.
We're not here to be the fun police here. We're just here. It's actually your meeting. You know, I wish I understood that. I don't. But let's continue, please.
Okay.
You're doing great.
All right. We'll continue for a little while longer, and then at some point, people's brains are going to explode. We'll stop just shy of that point. Okay. If you feel your brain like beginning to throb, please raise a hand. Okay. So this is how all of IO5 is going to work, basically. Like, and there's a bunch of different cases in here, right? Basically, one for every single one of the IO cases, right? So here's how we figure out what time it is, right? Like we call monotonic time. Here's how we figure out what execution context we're running on. Here's map. Map is actually interesting because, and actually let's go down to FlatMap because FlatMap is kind of where things get really, really fun. So I mentioned we had this continuation stack. Right? Well, so far we haven't needed the continuation stack. We've just been like interpreting IO pure or stuff like that, right? So what do we actually do when we need why would we need the continuation stack? Well, the reason we would need it is for FlatMap. So the shape of FlatMap is, and here's an example of it, right? It's like on the right-hand side here. The shape of FlatMap is you have an IO, and then you have a function that you're going to call when that IO finishes. So when you're done executing it with its result, you're going to call that function, and that's going to give you another IO. So that means that you need to take that second function and stash it away somewhere, because you're going to come back to it, right? Think of this like putting it on the stack, and then you call the IO, like that kind of a concept. But we're not on the stack, because we can't be on the stack, because we're going to get off of our thread. So where do we put it? We put it into the object state. So this is that continuation thing that we set up earlier. So here's the state of the FlatMap. Here's the IO that we're trying to execute. And here's the function that we're going to run once this IO is done. Okay? And so what we do is we take this F and we go down to the end of this inline pattern match that surprisingly makes the performance faster. Let's actually It's like a good, where do we bail out? Oh, here we go. So here's where we bail out. Basically, this is a special hot path for like some very specific cases of I/O that we just want to like execute immediately inline rather than sort of delegating to machinery. Turns out this is faster. I would not have expected that.
It has less than 7 cases.
It has less than 7 cases, right? So this actually lands you in a slightly different part of the jet, which is intentional. And that also means, by the way, that our I/O cases have to be very specifically ordered. Like if you change the ordinal of the tag, or if you make it non-contiguous, you're sort of sunk. Like if you sort of insert gaps in the tag, you're really in trouble. There's a whole like basically novel in a comment somewhere which says like if you're modifying this code, don't. Like it's just really, really, really dicey. Okay, so here's where we bail out. And what we're going to do is we're going to take that f, which is this function right here, right, the right-hand side of the flat map. We're going to take that f and we're going to push it into the object state. And then we push a continuation onto the const byte stack, which is the same sort of data structure, just more optimized. And that continuation is FlatMap k. FlatMap k is just byte 1. Okay? So then here's the idea. So we push that onto there, and then we call the run loop on the inner I/O, which in this case is rest. Right? So we call the run loop on the inner I/O. Remember back when we came all the way back up and we were looking at the implementation of pure and error right here, right? So these were the simplest cases. Well, when we're implementing pure, we have a value in our hands and we pass it to the succeeded function. What the succeeded function does is it pops the byte stack. So it gets the continuation from the byte stack and it figures out, well, what was the thing we were supposed to do once we got this value? And FlatMap k is right here. So this is the second half of FlatMap. Basically in the implementation, FlatMap got cut in half. One half of it ended up in run loop, the other half of it ended up in succeeded. And actually it's cut in thirds because there's an error case as well, right? But the error case is bail out, right? So when we're in FlatMap k, we call object stack pop, and we cast it to a function from any to I/O of any, because types are the devil at this point. And that gives us our f back. Now, in the interim, remember that I/O that we asked for, the rest, this might be doing some very complicated things. Like in this case, response is like calling to the internet. Okay? So this is a really complicated thing that's going to go off on different threads, and there's going to be timeouts, and then like there's going to be an asynchronous callback, and like maybe someday we'll come back to the same thread if we're like happy, right? Like so, this is complicated things happen in the interim between these two lines of code. We finally came back and we got our f back. And the reason, by the way, we were able to get our f back is because we know for each one of these continuation types, like each one of these bytes, we know how much state we pushed on the stack. So for FlatMap, we knew we pushed exactly one thing. For some of these other cases, we pushed nothing at all. And we know that a priori, so we can keep the stacks exactly in sync without inserting any messy checking logic. And if you insert any bugs, weird things happen because there's absolutely no guardrails on this stuff. That's what we call the function. So we call f of result. That gets our what this will return from the pattern match. That returns us an I/O of any. And remember, we called succeeded from run loop. Pure, which is down here, this is where we call it succeeded. And we just called run loop recursively with the result of that. So run loop then is tail recursive on the left-hand side of the calculation. This is also, by the way, how this whole thing is stack safe. So it's how you can write I/O programs that just loop indefinitely and you never sort of run on a stack. This is how it works. All right, pausing for questions.
How do you detect if there's performance degradation when changes are made, and like how do you maintain that?
Yeah, so the question was, how do you detect when there's performance degradations and how do you maintain it? We do two things. So we do what Armin calls armchair performance work, which is where we sit and think very carefully about it. We're like, oh, we know that ARM behaves like this, so like, you know, that type of a thing. Surprisingly, that gets us a lot of mileage. The second thing that we do, actually I guess we do three things. The second thing that we do is we have a very large micro benchmark suite. So we use JMH. Micro benchmarks are really dangerous, especially on stuff like this, because it's like, there's so much noise, like there's a lot of things that are going on, so it's really, really easy to misinterpret it. It's also, the micro benchmarks are looking through IO, so the performance is actually dominated by things that are not this, right? Like byte stack is fun, but we could have used an array there of like int, it would have been fine. The real hit is the allocation bio. So we do a lot of that stuff. The most useful tests there tend to be the scheduler tests, where we allocate just like tens of millions of fibers or hundreds of millions of fibers and let them go ham on like 24 CPUs or something like that. And like my liquid cooled like Ryzen gets very, very hot in my room. I'm the designated benchmark runner. We basically can't run them on AWS because it's too noisy. So we run them on my gaming machine actually. And that's how we performance test most of Cat's Effect. The third thing that we do is there's companies that like use Cat's Effect in production at very, very high scale. Like sometimes they'll deploy early versions for us. We can get like numbers on things. We look at Tech and Power sometimes. Like those types of end-to-end benchmarks, those are the actual meaningful thing. Like no one cares how fast your FlatMap is. They care how many milliseconds your endpoint takes to return. That make sense?
Yeah, thank you very much.
Cool. All right. So we are now at a fork in the road. And I think we probably have maybe 10 minutes of useful brain power left amongst all of us, right? So we can either go deeper, and we can look at the thread itself, and how do we schedule like these individual fiber actions on the thread such that it maps to the CPU, and like we balance that work and like keep it fair and keep it like low overhead, like all that. We do that, which is going to be like bit masking for days. Or we can stop bit masking, give ourselves a little bit of a break, pretend that all of those problems are solved for us, and we could look at like HTTP frameworks and like other higher level things that are maybe more useful than how I spend my time. Strong opinions? Bit masking or HTTP? Bit masking? I know what you want. Bit masking? Anybody gonna vote for HTTP? No? More bit masking?
Do you have any way to learn about the bit masking, like on video or something that you're watching?
That is an excellent question, probably the best question. So the answer is no to the video, but yes to the ways to learn about it. And the way you can learn about it is clone the Cat's Effect codebase, and then open up workerthread.scala. There are 3 versions of it. Open up the JVM one. Workerthread.scala and also workstealingthreadpool.scala, also open a JVM one. The comments in it are like a book unto themselves. I can't take any credit for it at all. It was all the seal, but it's very, very, very well commented. It's very clear. And if you just read through the comments, like you'll understand it. And I know this is true because I didn't write work stealing threadpool. The seal did. I had no idea how it worked, and I learned how it worked by reading these comments. So, work stealing threadpool.scala and workerthread.scala. IOfiber.scala is the other fun one, but like, there you go. The comments are actually good. We do like religiously keep them up to date because we know that when we come back to this code in like a month, we will have no idea what's going on if we haven't written ourselves a thesis about it. Good question. Okay, does that mean you're voting for HTTP? Or okay, you're one vote for HTTP? HTTP2. HTTP2. Okay, I'll compromise and I'll show you the bit masking thing that we just talked about, and then we're going to go to HTTP. All right. Work stealing threadpool. This is the file that I just told you to open. This is the JVM one. Like I said, it just does all of the things. This is an execution context. So it's an actual thread pool, and it's going to maintain inside of it a number of worker threads. These worker threads are the other file I told you to open, and these extend thread. Okay, so these are the things that are doing the actual work. Like if you're looking for like where does where do the syscalls happen? Where does the like bytes move around? Like stuff's going to happen in here. And in particular, if you go to the run function, I told you there was a novel. This whole thing is basically how it works. So it's a very complicated state machine. It's actually about to get a lot more complicated because we're putting more stuff into it. But right now, the current version of it is not sort of too horrible. But it basically runs through, and it's sort of a 64-step state machine where I think 61 of the steps are all the same. So it's like pretty straightforward. There's a couple of data structures in here that deal with sort of your local work queue and your global work queue. And there's a lot of like very subtle math that's associated around like how do we know that this is both fair and high performance at the same time. A lot of this thread pool comes from a port of Tokyo, which is an I/O framework in Rust. It's really, really, really good. And Tokyo, in turn, was porting and modifying the runtime of Golang. So Golang, Tokyo, Cat's Effect, and Zio are basically the most advanced asynchronous runtimes in sort of the public, general asynchronous runtimes in the public space that I'm aware of, basically because of this functionality. Cat's Effect is almost the same as Tokyo, except it has a more batched spilling mechanism, which is a little bit better in terms of performance. Okay, this is where you look for the bit masking layer. Time for HTTP. So now that we totally understand all of this, and we know how I/O works, well, that's actually kind of cool, because now we have a machine where we can do a bunch of interesting things with code, like to sort of construct these programs, right? We've got sort of pure, which we already looked at, and FlatMap, and we all know those are the two most important functions. We've got async, right? Like async is a thing that, I didn't show it to you, but like it's in there, go look it up. But like this is how we would actually do like asynchronous I/O, wrap up callbacks and things like that. So now we have a machine that can actually execute these things extremely fast for us. Now we can start building stuff with them. And in particular, we're going to build one low-level primitive, and then we're going to use that to build a whole bunch of other things. Okay? And the low-level primitive we're going to build is resource. Okay? So go up here. So resource is kind of, we saw it earlier, and I told you not to worry about it, but now we're going to worry about it. So in this code right here, what we're calling is Ember Client Builder. Okay? Now this actually almost looks comfortingly benign, right? Like this is probably not some crazy functional programming thing. This is probably just like a builder. And lo and behold, it is in fact a builder. So this is great, right? Like it's not confusing. So Ember Client Builder, and it has like a bunch of state in it. And what did we call, right? Let's shift this back over here. I guess we call default. Okay, so default, oh good. This is totally a builder pattern. Like we don't even have to like spend a lot of time explaining this. This is super easy. So new Ember Client Builder, and then we call build. Okay, so build is over here. Uh-oh, now we're starting to get to stuff we don't understand. Okay, so the first thing we don't understand, which we haven't really talked about, is this F nonsense here, right? So, what does this mean? Well, in our context, this just means I/O, okay? Most libraries in Cat's Effect are written using a polymorphic style. This is sometimes inaccurately called tag final. It's just polymorphism, that's all it is. F is an artifact of that, and it basically means HTTP4S can work against Cat's Effect or Zio or whatever YOLO Town monad transformer stack you want to build if you're feeling sadistic, right? So all of that actually functions, and this is how it works. But in our case, F equals I/O, and in 99% of the code you will ever see in your entire life, if you see F, substitute I/O, because that's probably true. Okay? All right. So build resource of I/O, remember, returns a client of I/O. Okay. And now we're doing for comprehensions. Okay. For comprehensions, desugar into FlatMap. And FlatMap, at least on I/O, we know what that does. That's going to make an I/O, and then we're going to end up in run loop, and it's going to push to the continuation stack, and it'll pop from the continuation stack. So okay, we really understand FlatMap now. But this is FlatMap on resource, which we haven't talked about. So what is resource? Resource, the technical term for this is a code density mode. That helped no one. It didn't help me either. Like it took me a very long to figure out what this was. So what resource does is it wraps up effects like I/O and then allows you to flat map over them, carrying with you a finalizer. So the idea is, imagine something like opening a socket. Okay? So when you open a socket, you want to make sure it gets closed. But you don't really know at the point where you open the socket all of the code that you're going to use to do things with the socket, right? Like really ideally, you want to open the socket and then throw it over the wall, and then somebody else decides what to do with it, and you just have a guarantee that whenever they're done with whatever they're doing, it's going to get closed. Resource does that for you. I/O does not. Okay? I/O is very, very strict about this. So resource is implemented in terms of I/O, and it implements this functionality for you, and it's really, really, really useful. So what this is called is a dynamic resource scope. It sort of scales out with FlatMap. This is in contrast to what I/O implements, which is a static resource scope. You have to put it inside of a bracket. That's the technical jargon for it. So how does resource work? Well, it turns out that resource, as a code density monad, is also a sort of free monad. So now we're looking at something that's a little bit closer to how we used to implement finalizers. Because once we got to this part of the stack, we were exhausted, and we were like, we don't care about performance anymore. So pure returns pure. Like if I go to FlatMap, FlatMap is going to return bind because I guess we were feeling Haskell-ish. And these are just sort of your standard free monad type functions at this point. Yes?
Did you choose that implementation to prevent having quadratic performance gateway between FlatMaps like we do in Haskell?
Oh, you mean the fact that, so this is a very solid question.
Could ask concurrency to prevent having quadratic ID costs.
Yes.
And then we compose the whole thing when we want to have a function at the end of it when we be sure that we don't want to change frequent stuff.
That's correct. So yes, the encoding is to avoid that cost, basically. So we basically, what's being pointed out here is that the implementation of concurrency in Haskell looks very, very different than this, and basically it sort of associates things in slightly different cases. The implementation of concurrency in Haskell is a lot closer to how you would derive it from category theory. But if you do that on the JVM, or actually if you do that in Haskell, like all sorts of weird pathologies sort of fall out of it. So it turns out by reassociating the structure to here, you sort of get the composition here on the fly. And you avoid some of the performance costs that happen when you actually run it. Really, really good question. Okay, I can see that brains are fading, so I'm gonna hurry up. So resource basically builds this data structure, similar to how we did with I/O, but then inside of resource are these like, there are I/Os inside of here. And then we will run the resource, I'm gonna go back to main, we will run the resource when we call use. And when we run it, we're actually gonna produce an I/O. So it's not actually running, all the running is done by I/O. This is just a fancy way of building I/Os, is basically what resource is. And it's going to do that in a really, really complicated way. But actually, I think it's full. Yeah, here we go. So it basically does this, which we're not going to spend a lot of time talking about. But the TLDR is it kind of does the thing that you might imagine it does, right? So remember, the whole point of this was to you allocate something and then you have a finalizer for it, and then you can call FlatMap any number of times you want, and then eventually you stop. And then the finalizer should write that time. So this does the thing you think, right? It runs the first thing, and it holds onto the finalizer and runs all of the flat maps in the middle, and eventually you get to the end, and it runs the finalizer. Okay? I'm gonna speed up again. All right, scanning through this super, super fast. By the way, if you want to look at all this stuff yourself, I cloned these repositories. Okay, so I actually don't have anything fancy going on. I literally just called git clone on catseffect, fs2, http4s, and keypool. These are all under type level except for http4s. And you can find all of the source code yourself. But keypool builder is basically where we're building a connection pool. Okay, so the request key is going to be basically the domain, and the Ember connection is going to be the thing that actually manages the connection. We do a whole bunch of stuff with that, with client helpers, which I don't think you're going to get a chance to see. And we return the builder. You mentioned HTTP2. I am here to disappoint you and say that in default, HTTP2 is disabled. So sadly, we won't be talking about it. But Ember does actually support it, and HTTP2 is cool. Okay, so we've gotten down to the part where some stuff starts happening. But the air conditioning has been off for an hour, and I think our brains have been off for longer than that. So I'm calling a halt because I'm getting tired. Any last questions? Yes?
Can you specify Q equals Q?
Yeah, that's all the way back there. That's a great question.
It's Q not equal to
So, when we first released catseffect, we made a mistake. We defined this as a trait. We should have defined it as an abstract class. The reason this is a problem is because we can't add fields to it without breaking separate compilation. Okay? Now Q is a field, and it has to be a field. There's no way around it. And the problem is, if you have a version of code, if you have some code that was compiled against a version of catseffect before this Q field was introduced, and then you have some new code that's using a new version of catseffect that links against this code that was compiled against the older version of catseffect, this code will break. because the field will not be there. Basically, it'll be evicted forward, but the constructor will come from the old version of cat's effect, and the code touching queue will come from the new version of cat's effect. So basically, you'll have the definition, but you won't have the instantiation. So what do? Like, can we at least maybe detect this so that things don't crash on users, which is actually what happened when I painfully discovered this? Well, as it turns out, yes, we can. So Q equals Q. When Q is not equal to Q is when this separate compilation thing has happened, the first Q will be null, and the second Q will be array blocking Q. When you compile everything at the same version, though, they're both array blocking Q, and it's fine. So that's why we have this warning right here. Great, great question. Any other questions?
Why the name?
Why the name? Cat's effect? So originally, I was thinking about Scala Z effect, actually, which was a submodule of Scala Z that dates back to Scala Z like 6 or something like that, right? And Scala Z effect had I/O. One of the big problems with cats back in 2016 was that it didn't have an I/O monad. It didn't have a task. It didn't have anything. And so people were stuck. They wanted to move off of Scala Z, but they couldn't because there was no I/O. So I wanted to choose a name that people understood. We're long since past that context, so now it's just confusing, but that's the recipe system. I think it was another question?
Are you planning a new major release of cat's effect, like 4E written against Scala 3? Is there some things that you would do there that you can't do with Scala 2?
Yes. So the question was, are we planning a new major release of Scala, of cat's effect? So we're not planning it, sort of. We like to dream about it when we get very frustrated by compatibility guarantees. There's a lot of stuff that I would change about cat's effect now that I've sort of done 3 once through and I've learned all the sort of failings. We can go into that, that'd be really fun. So I break all of that. As far as what we would do with Scala 3 that we can't do with Scala 2, this is, by the way, the plan. It's like the next, like Cats 3 and Cat's Effect 4, respectively, will be Scala 3 only in some years, whenever we do that. There's some differences in the type class encoding, like being able to use given a little bit more directly actually helps us out a lot. But a lot of, I think, what we would change is really just more stuff in Cat's Effect that I would like to break, that I don't think is quite correct.
So like you change around the hierarchy of the type classes, or?
We would probably, I don't think we can flatten out the type classes because Martin's coherence proposal didn't land, but I don't know, maybe it will by that point. At which point, yeah, we'd be able to flatten out the type classes into a more reasonable structure, right? Like clock wouldn't be orphaned, and like you wouldn't have this weird sort of temporal goes to async, but then sync is over here. Like that's kind of an odd thing going on. So that's one example. There's other stuff, like auto seeding is something I want to give more control over. Good question. Yes?
Does the project Loom virtual thread have any effect for FlatMap?
Has Loom had an effect on Cat's Effect? The answer is yes, in that the question comes up a lot, but no in any sort of real sense. So virtual threads are slower than fibers. I haven't looked into why that is, but I think their sort of coroutine implementation isn't quite as optimized. They'll get there. Like they'll eventually be as fast as fibers, but for right now, it is actually quite a bit slower. It's not really the sort of right level of abstraction in a lot of cases. Like sort of Cat's Effect is sort of doing this sort of very high level abstraction over here, and then you want to sort of compile it down to something. Loom's implementation is kind of at the wrong layer for that. And then there's other problems like interruption and resource safety, which like Loom actually makes worse. So we've tried doing some experimenting with it. We have some code in there right now which does fiber tracing a little bit differently when you're on Loom so that we don't just crash you. So that's kind of subtle, but right now we're not taking advantage of it anyway because every time we try, it just ends up being worse. So, good question. And then there was another one?
Yeah, I want to ask, what are the reasons to come up with your own works in full instead of using, for example, from drawing? Why is it the changes in this still work is not kind of duplicated? Why do you reinvent all the time?
This is a great question. Basically, why not use fork join pool? Why not just use work stored simple? The answer is fork join pool is very slow in some cases. It basically does 2 things that I don't like. So first off, the local queues are unbounded. It doesn't have an external queue. that causes a whole bunch of very specific problems that I think are just sort of not ideal. I would rather have valid local queues. The second problem, which is more annoying, is that fork join pool is kind of trying to be a least common denominator thread pool. So it does things like what Zio introduced recently, where it sort of detects blocking and like detects compute bounding and things like that, tries to dynamically resize the pool. That makes sense if you want to be the be-all, end-all thread pool, and if the only abstraction you have is execute runnable. But for Cat's effect, we don't want that semantic because we want to have exactly this number of threads, no more, no less. And if you want another thread, you should do blocking. Like we want to be really explicit about it. So we're faster than fork join if you use us one-to-one because of the local queue thing, because it's built from Tokyo. But it's not faster by an amount that matters. But the main thing is the control over the thread pool size. Good question. Anybody else? You and you.
So a presentation about Optimus and Cat's effect, and they're a little different. It seems like Cat's effect is more explicit in declaring the I/O, while Optimus is a little bit more implicit.
Yeah.
What are the pros and cons on each?
So they're really trying to solve different problems. So Optimus is a managed platform, right? And it's designed for a very specific company and a very specific training clientele and things like that. And if I had that type of problem space, I would build something like Optimus. It's just better. Cat's effect is broad, like our market is sort of the internet, right? So like it's meant to solve a lot more problems. Optimus also has like more rich things around sort of computational graphs and other things like that, which Cat's effect just doesn't even try to do. Like you have to ask for parallelism, for example. I think the biggest ergonomic thing that you might notice between the two is that Optimus prescriptively says we're going to use direct syntax with uncolored functions, mostly, and Cat's effect is like we're using monadic syntax with very, very strongly colored types and functions. And I think the latter is something that I would like to massage a little bit. Like I'd like people to be able to use more direct syntax with Cat's effect because I think for comprehensions are confusing sometimes, and like nobody likes the star arrow syntax except the Haskellers. So I would like to kind of blur that together just a little bit. But the coloring is probably here to stay, which would be a major difference. Does that make sense? Yeah.
Do you have any like optimizations around the like bad flow pattern, specifically doing like unsafe perform, whatever, unsafe perform IO, like if someone does it,
yeah,
you try to make it fun.
Actually, yes. So there's a couple of things. The first thing we want to make sure is if someone does an unsafe run sync, it doesn't starve their application. So we wrap it in the block context from Scala, which is something from the Scala standard library. Akka introduced this, and that allows us to treat it as a blocking, which is kind of nice. And it sort of uses the same mechanism. So that's kind of the first thing we do. The second thing we do is we actually very explicitly try to encourage people to not use like if you're going to do unsafe things, don't use the unsafe runs that are on I/O, use the unsafe runs that are on dispatcher. And dispatcher is this other completely different thing, which is basically a way of unsafely running defense. So when you're doing like asynchronous callback code or like reactive streams or something like that, you basically can't avoid stuff like this, like running, I've heard it called Soviet interrupt, right? Like when unsafe code runs you. Right? So these are actually faster than the I/O variants because the I/O variants do a bunch of bookkeeping around fatal exceptions. This one, we know there's an outside I/O context, so we don't have to do that, and we do actually try to optimize the crap out of this one. Cool. Yeah, good question. Anybody else want to prevent us from fleeing for air conditioning? Thank you so much.
Thank you.